Welcome to Module 3, Finite Control Volume Analysis. In this chapter, we'll be applying mass and linear momentum conservation for systems of finite size. This basically involves the balance of inflows, outflows, as well as volumetric generation or extinction of mass or momentum within a system. You may recall that in the previous module, we had discussed the Reynolds transport theorem, which I am going to state here. Reynolds transport theorem, which may be stated as if you have any arbitrary extensive property B, the corresponding intensive property lowercase b is defined as B divided by the mass of the system. This is the intensive version of the same property. Okay. Example could be, we can have B to be linear momentum, lowercase b would be velocity. You can have B to be mass, lowercase b would be simply 1. You could have B to be the total energy of the system, lowercase b would be the specific energy of the system. Now, what is the Reynolds transport theorem? It says the rate of change of B within a system, the total derivative of B with respect to time, is equal to the partial derivative of the B of the quantity B within the control volume, or the rate of change of B within the control volume, plus the sum of the fluxes of the quantity B over all the surfaces, over all the inlets and outlets. Now, what do I mean by that? I can have an arbitrary shaped control volume. Okay, the surface bounding the control volume or separating it with the surrounding is called the control surface, and on this surface I could have an arbitrary number of inlets and outlets. So I'm going to just draw a few inlets. I'll say I1 and say outlet O1, and I'll say inlet I2 and I'll say outlet O2. I could have any number of inlets and outlets. This term here, the integral over the control surface of the quantity B flowing across the area is the flow rate, of B across the control surface, or it can also be stated as the flux of the quantity B, quantity lowercase b across the control surface. Now, it's not an unfamiliar property. You have seen this many times before. Like, for example, if uppercase B is the mass and lowercase b equals 1, integral rho times 1 v dot dA is simply the mass flow rate across a surface. Okay, you could recall that if it's an incompressible flow, rho is constant for an incompressible flow. And integral v dot dA times rho is simply rho times the volume flow rate, which is mass flow rate. Okay, this is the mass flow rate. And Q is the volume flow rate. Okay, now if B were momentum, mv, lowercase b is simply velocity, and this quantity here, integral rho times v dot dA, represents the momentum flow rate across the control surface. Now, we have seen this before. I'm just trying to recall all this. Okay. Now, you could have this a control volume which has multiple inlets and outlets, okay, it would have multiple inlets and outlets, and this integral here, so this could be a1, a2, a3, a4. What I write as rho times b v dot dA can be split into multiple integrals over a1, over a2, and so on. Okay, we'll see this in the form of problems. So now where are we? So we come back to applying Reynolds transport theorem for mass conservation. If we try to do that, what is mass conservation? If you have a system of fluid molecules, if you call all the molecules in this all these molecules, if you call them to be one system, the mass of the system is a constant. That is what mass conservation is about. Mass cannot be created or destroyed. If that is the case, the total derivative of mass with respect to time should be 0. Okay, this is just simply basic physics. Mass can neither be created nor be destroyed in a classical physics context. So we take our Reynolds transport theorem, which is dm system over dt equals the partial derivative of the mass that's within the control volume plus the integral over all the control surfaces or all the inlets and outlets of rho times v dot dA. Now what is mCv? That is the density of the fluid times the volume of the control, the volume occupied by the control volume. So you can simply also write this as rho times volume plus integral over the area rho times v dot dA. Okay. Now, why do I put 0 here? 0 is because the mass of the system doesn't change with respect to time. So this is the relationship for mass balance or mass conservation over an arbitrary control volume. Okay, you can apply it for control volumes of any shape. It doesn't matter what the shape or whether the problem is steady or unsteady. Now this equation, I'll rewrite it here, rho times v. So instead of writing v, I'm going to write this as dv and integrate it. I'm going to go back a little. Let me start again. So I have d over dt rho times volume plus integral over the area or control surfaces rho v dot dA equals 0. Now I'm going to write rho v as the integral or triple integral over the control volume rho times dV, because this allows for density to be a position of space within the control volume. There is no restriction that density has to be constant or just be a single constant inside the control volume. So if I rewrite this, I have the partial derivative of the triple integral over the control volume rho dV plus the double integral over the control surface rho v dot dA equals 0. This is your key equation. Okay, this is the all-powerful mass conservation relation that we are going to use for solving problems. Now, what are some of the special situations that we can think of? So we are going to go to the next page. I'm going to restate the equation. Partial derivative with respect to time, rho dv plus over the control surface, rho v dot dA equals 0. Now, if we have a steady flow wherein there are no time dependent effects, we can simply discard the first term and the mass conservation relation becomes rho v dot dA equals 0. Okay. This can also be written simply as, since if you take a particular particular area A1, rho v dot dA is the mass flow rate across the area 1. Okay, or in general you can write this as over AI is the mass flow rate across that area. Okay, so now I can generalize this relation as, I can split this integral as the sum of all the inlets minus sum of all the outlets equals 0. This is true for a steady flow. It does make sense because if you have like a system in which there are inflows and outflows, the sum of all the inflows must balance the sum of all the outflows if you don't have any accumulation or volume change in your control volume. So the quantity here, integral v dot dA, you can think of it as the volume flow rate. Okay, we can also think of it as, if you take the volume flow rate, that is if you take a cross section and let's say you have a variation of velocity with respect to position. So suppose the velocity has a profile that varies with r. You can think of what is the volume flow rate in this situation. You can also think of a similar situation where you have a flow with uniform velocity. Let's say v bar, but has the same flow rate and the same cross section. So whatever your cross section is, let's say this is A, it's the same cross section here. In both cases, the flow rate and the area are the same. So if you think of it, q dot, which is integral v dot dA, is also equal to the average velocity times area. Okay, so I can define an average velocity as integral v dot dA divided by integral dA, or simply A. Let me go back a little. I'll just write this as A. So a summary of the of this discussion can be found in section 5.1.1 of the textbook. Okay, so please read that section and to revise these concepts. Now, one closing remark that I would like to make is, how is this integral v dot dA calculated? Okay, so in general there is a sign convention. So if we have a control surface, like for example, let me draw something arbitrary. If I have this surface, we always associate a normal to a surface as the direction perpendicular to the surface. Okay, that's why it's called normal, and this normal is always drawn outward. Normal vector is drawn outward to the control volume. Now if we think of this surface, and let's say its area is A, the vector A is the magnitude A times n cap. And when I say dA cap, I'm talking about an elemental area dA multiplied by n cap. Now through this surface I could have the velocity going in an arbitrary direction like V, in an arbitrary direction V, and I would have V dot dA or V dot dA to be positive in this case, because they are parallel to each other, or at least they are in the same directional sense. Now I could have this other surface where I have the normal vector, and then let's say the velocity is going in. Here I would have V dot dA or V dot dA to be negative in this situation and positive in this situation. Okay. Now what is the implication for that? So I have integral rho V dot dA. This is what I want to evaluate, and this integral would be V dot dA would be positive for an outflow, and V dot dA would be negative for an inflow. So you can, if you remember the sign convention, that if you have an area, the vector is always drawn outward. Inlets are negative and outlets are positive. Okay, we'll see these through some examples. Okay, so let me go on to section 5.1.2, where we look at a fixed non-deforming, meaning shape doesn't change, non-deforming control volume. Like for example, I'm going to look at example 5.2, where we have a pipe flow, where we select a cylindrical portion as our control volume, and through the section 1 and section 2, and there is also the curved section which I'll not give a number, but I have section 1 which is an inlet, and section 2 that is an outlet. The flow comes from left to right. Okay, I have an incompressible flow. Okay, let me read out the question. Air flows steadily between two sections in a long straight portion of 4-inch inside diameter. So the inside diameter is 4 inches as indicated in the figure. The uniformly distributed pressure and temperature at each cross section are given. So P1 is 100 psi absolute, T1 is 540 degrees Rankine, P2 is 18.4 psi absolute, there is a drop in pressure, and T2 is 453 degree Rankine. The velocity at V2 is given to be 1000 feet per second, and we are asked to solve for the average velocity. We are asked to solve for the average velocity at V1. V1 bar is required. So what is our solution steps? The first step is to state the mass conservation. So we have partial with respect to time, integral over the control volume, rho dV, plus integral over the control surface, rho V dot dA equals 0. Now recall, what is your control volume? Your control volume is a cylinder. Your control volume is a cylinder. draw this as the axis. Okay, the control volume is the cylinder. You want to mark this control volume, and then this is your control surface, CS1, CS2, and then control surface 3. Now, first of all, this is a steady flow, which means the time derivative is 0. So we can just drop the first term. Okay. Secondly, I have the integral, or that leaves me with integral rho v dot dA equals 0, which I'm going to split as CS1 plus integral over CS2 plus integral over CS3 equals 0. Now, if I take CS3, this is the curved surface of the cylindrical control volume, and the velocity across that surface is obviously 0. So this term, which implies v dot dA, whatever that integration is simply 0 because velocity is 0. So I can strike this out. Okay. So I'm left with the surface 1 rho times v dot dA plus integral surface 2 rho times v dot dA. Okay. Now this is equal to 0. Now, we do know that v dot dA is the average velocity. Okay, we are given this at section 2. This is the average velocity at section 2, and integral a1 v dot dA is the average velocity at section 1, which is what we are trying to solve, and this is given to us. Okay. The other thing is rho at section 1 and rho at section 2 are assumed to be uniform. I'll write this in the next page. Rho 1 and rho 2 are assumed to be uniform across the cross sections 1 and 2 respectively. That implies that I can write it as rho 1 times the average velocity at section 1 minus rho 1 at times the average velocity at section 1 plus rho 2 times the average velocity at section 2 is 0. Now why the minus sign? I have my inlet section 1, I have my normal pointed outwards and my velocity pointing inwards. So I have v dot dA equals v dot n times dA. Now, even if you don't do very serious vector algebra, you could say that if v and n are exactly opposite to each other, this quantity is less than is basically minus v. Is basically minus the magnitude of the velocity. Okay, so I have rho 1 v average 1 equals rho 2 v average 2, which you could have also written as simply m dot 1 equals m dot 2. Okay, so if we want to solve for the average velocity at 1, that is simply the average velocity at 2 times rho 2 over rho 1. Now instead of providing us rho 2 and rho 1 directly, the problem tells us the pressure and temperature, for which we can use the ideal gas law. P equals rho RT or rho equals RT over P. It's the same gas, so R is the same. So we can write rho 2 over rho 1 equals RT2 over P2 times P1 over RT1, or this is P1 over P2 times T2 over T1. So I have V average at section 1 equals V average at section 2 times P1 over P2 T2 over T1. You can substitute the numbers and check against example 5.2 in the book. Okay. Moving on to Newton's second law, or deriving momentum balance for control volumes, we start with stating Newton's second law, momentum balance for control volumes. In this case, our extensive property B is momentum and the corresponding intensive property is velocity. We write dB system divided by dt is the partial derivative of with respect to time integral rho b dV over the control volume plus integral over the control surface rho b v dot dA. Okay. Now, I told you that our B system being mv, what is d over dt of mv? According to Newton's second law, this is sum of all the external forces acting on the system. So on one side we have d over dt integral of the density times the velocity dv plus integral over the control surface rho v dot dA, and this is equal to, for mass conservation we had the right side to be 0. In this case it's going to be sum of all the external forces. Okay, so this is the broadest statement that you can make for the conservation of linear momentum over a control volume. So how do we write this here? So this is also same as equation 5.22 in the book, where it is written as integral, the same thing, integral over the control volume v rho dV plus integral over the control surface v rho v dot n cap dA, and that is equal to sum of all the forces over the contents of the control volume. This is equation 5.22. I'm just repeating it from the book in their notation. Okay. Now we want to consider some special cases, like for example, what happens if we have a steady flow? That is, if you have a steady flow, the derivative with respect to time is 0. So we have integral over the control surface rho v dot dA equals sum of all the external forces. Now what is this quantity? This is v dot dA, or this is the volume flow rate, a scalar. This quantity here is also a scalar, and velocity of course is a vector. So what you have on the left side is a vector. It is specifically the flow rate of momentum. Flow rate of linear momentum. Okay. On the right side here, you have this term, which is also a vector because it's a sum of forces. It has to be a vector. So we are equating a vector to a vector. Just wanted to highlight the point that the left side, even though it has multiple vectors, it is just a vector multiplied by two scalars. Okay. So let's consider an example to illustrate the momentum balance equation that we just saw. Okay. So here I have a nozzle. Okay. I have a nozzle that's ejecting water, okay, at a velocity v1, and the cross section area of the outlet of the nozzle is a1, and that is equal to 0.06 square feet. This is example 5.10 from the book. Okay, and then I have a vane that is curved, okay, and the angle is theta, and I have here the vane, the water flowing along the vane and changing its direction in order to exit the vane or leave the vane at an angle theta with respect to the horizontal. So if you consider that the area of the flow is the same, I'll just change my diagram a little. Okay, if I consider this to be also equal to a1 and the velocity is v1, I need to calculate what is the force that is going to act on the vane. Okay,